Good morning, students. Everybody is okay.
Yes, sir.
So last time we have covered the basic elements of the twin system. So we have seen we have the basic element as a population of the prospective customer, arrival pattern or distribution of the inter-arrival time, then the queue discipline, service mechanism, distribution of the service time, right? Then state of the system we have covered. Then we have seen the few performance indices. Now next is the very important one, Poisson process. So Poisson process, here we define the random variable xt, the number of occurrences of event in an interval 0 to t. So here, if I'm taking the time interval 0 to t, right? So let's say it is t, it's t, it's t. Number of occurrences. If we have the number of occurrences, right, at any moment. So number of occurrences, here we have the xt is equal to 3, xt is equal to 3 and xt is equal to 2. So what is this? This is the random variable, or you can say it is the discrete random variable. So when we take the random variable, the number of occurrences of events in an interval 0 to t of length t is a random variable having the Poisson distribution. Means here the xt follow Poisson distribution with parameter lambda into t. With parameter lambda into t provided xt satisfy the following axioms. So what are the axioms? Here the axiom 1 states that yt be number of events occurring in an interval t1 to t1 plus t, t1 and t greater than 0, and xt defined above, then xt and yt have same distribution. What is the significance of this? If I take, let's say, if this is the time interval, let's say this is the t1 and this is the t1 plus t, and here the occurrences are happening, right? Here the occurrences are happening, here the occurrences are happening, and number of occurrences whatever we are counting, that we denote as a yt. So let's say yt is equal to 3, yt is equal to 1, yt is equal to 0. So again this is the random variable. So the first axiom is that whether you take the xt or yt, if the interval length, is t, if the interval length is t here, if the interval length is t, right, if the interval length is t, then we say xt and yt both follow, xt and yt both follow the Poisson distribution with parameter lambda into t. That is the axiom of homogeneity. Means it depends only on the time interval when we are observing, that is immaterial. In which interval we are observing, that is important. So this the first axiom is known as the axiom of homogeneity. Now second one is, if x1 x2 if xt1 xt2 and xtr be number of events occurring in r disjoint time interval of length t1 t2 tr respectively, then xt1 xt2 xtr are independent random variable. Means this is the axiom of independency. What is the significance of this? If we have the timeline and we are taking the different disjoint time interval of length different length. Let's say this length is t1, this length is t2, this length is t3, and this length is t4, and here the occurrences are happening, right? Here the occurrences are happening, and that count we are denoting as a xt1. So let's say it is the xt, right? So xt1, it's the xt2, it is the 4, xt3, that is the 1, and xt4, it is 2. So here what? This xt1, xt2, xt3, xt4 all follow the Poisson distribution. Now they are saying that these random variable are independent to each other. Means there is no effect. What happened in past, what will happen in future. So here it is written here that xt1, xt2, xtr are independent random variable. So this is known as the axiom of independency. Then we have axiom 3, also known as the axiom of regularity. In this, probability of no event occurs in an interval t to t plus delta t or 0 to delta t is equal to 1 minus lambda delta t plus higher power of the delta t. Higher power of delta t. Right? This is. So here what we have, let this is the timeline. Somewhere we have the t, and besides this we have the t plus delta t. It means this length is what? This length is the delta t, and this is very small. This is very small. Now, now they are asking what is the probability that there is no occurrence. Means in this interval there is no occurrence. No occurrence means, so first what we have to do? First we have to take what is the x delta t. Xt, number of occurrences, they are asking it must be 0. There is no occurrences. Now what is the probability of this? Right? We define the random variable that count the number of occurrences in a small interval delta t. Now they are saying that it is equal to 0. So we know that the x delta t follow the Poisson distribution, right? From the first we have seen it follow the Poisson distribution with parameter lambda into delta t, with parameter lambda into delta t. So probability for x delta t is equal to 0 will become, what is the PDF of the Poisson distribution? We know that e to power minus lambda to power t, lambda to power x upon factorial x, right? So e to power minus delta t, lambda delta t to power 0 upon factorial 0. So this will become e to power minus lambda delta t, which can be written as 1 minus e to power minus e to power 1 minus 1 minus lambda delta t, right? Plus plus lambda delta t whole square upon 2 factorial 2, and so on. So what is this? Here, because delta t we are taking very small, delta t we are taking very small, so these number are very very small, so we can say it is the higher order of the delta t, or it is equivalent to 0. So this will become 1 minus lambda delta t plus higher order of the delta t, and that we assume as a 0. So that is written in the first part. Probability no events occur in an interval t to t plus delta t or 0 to delta t, that is the p0 delta t, right? P0 delta t is equal to 1 minus lambda delta t plus higher order of the delta t. Is there any doubt in derivation, in understanding? Is there any doubt? Means this is nothing, this is the p0, right? P0 delta t. Now, second part, probability exactly one occurrence of event in the interval t to t plus delta t is equal to lambda into delta t, right? Lambda into delta t plus higher order of the delta t. So what are they are saying that? Again the same thing. Somewhere we have the t and here we have the t plus delta t, where delta t is small. It is very small. Now they are saying that in that small interval there is exactly one occurrences. In that small interval we are saying that there is exactly one occurrences. So again we define x delta t as a random variable. We want this is equal to 1, and then we have to determine the probability of this. So it is nothing, it is the p1 of delta t, p1 of the delta t. And by the we know that what is the pdf of the or probability point probability function of the probability distribution. Here the x delta t follow the Poisson distribution with parameter lambda into delta t. So pdf will become e to power minus lambda delta t to power 1 upon factorial of 1. So this can be written as lambda delta t into 1 minus lambda delta t plus lambda delta t square upon factorial 2 and so on. So which can be written as lambda delta t plus higher power of the delta t, because when we multiply delta t and delta t here, it will give you delta t square. Delta t square means higher power of the means the small quantity, and the small quantity we can assume as a tends to 0. So this will become lambda delta t. Then after in the third we have probability more than one occurrence of event in the interval t to t delta t is equal to the higher power of the delta t. So what they want in this, here we have the t, here we have the t plus delta t. They want more than one occurrences, means in the small interval they want more than one occurrences, means number of occurrences we denote by the x delta t, right? Number of occurrences we denote by the x delta t, and they want this should be greater than 1. And what is the probability of this? So it can be 1 minus probability of x delta t is equal to 0 minus probability x delta t is equal to 1. We know that total probability is equal to 1. Total probability is equal to 1. So if you subtract the for the 0 occurrence and for the 1 occurrence, you will get the probability for the for more than one occurrences. And this can be written as 1 minus. From the above, we have this value 1 minus lambda delta t plus higher order of the delta t, 1 minus lambda delta t plus higher order of the delta t, minus from here we have the lambda delta t plus higher order of the delta t. So minus lambda delta t plus higher order of the delta t, higher order of the delta t. So this will give you higher order of the delta t, that is the tends to 0. It means here in the Poisson process, let us first complete, then I explain that part. So this axiom is known as the axiom of regularity, where delta is the small quantity and higher delta t tends to 0 as delta t tends to 0. The collection, now we are defining the Poisson process. The collection of random variable xt, whatever the xt we have defined above, collection of random variable xt t greater than 0 which satisfy above axiom has the Poisson distribution called the Poisson process. Poisson process is nothing, it is a collection of such type of the random variables. So here in means if any process follow the Poisson process, it implies that at the particular small interval always we assume either there is zero event or at most one event. Never we can assume that we have more than one event from this theorem, from this axiom. Clear? Now we know that we have assumed that xt follow the Poisson distribution with parameter lambda into delta t. So what is the expectation of this xt? We know that it is the lambda into t. Whatever the parameter, that is the expectation of the Poisson distribution. Right? Now, if you compute expectation of xt upon t, so it will become lambda t upon t, that is the lambda. So what is this? It is the expectation of xt upon t is equal to lambda. And this lambda is what? It is the mean arrival or mean rate, not presently arrival, mean rate of occurrences. Mean rate of occurrences. Right? Lambda is the mean rate of number of occurrences in interval t divided by t. Right? Number of occurrences in interval of length t divided by t denote mean number of occurrences. Clear this part? So here mean number of occurrences in a unit time, lambda is called the mean rate of occurrences. Then earlier also we have studied this additive property of the Poisson distribution. If x1, x2, xn are independent Poisson variate with parameter lambda 1, lambda 2, lambda n respectively, it is given to you xi follow the Poisson distribution with parameter lambda I, and you are defining the another random variable x, or here say s. Right? Let's say s you are defining as the sum of n independent Poisson variate. Sum of n independent Poisson variate. Then s also follow the Poisson distribution with parameter lambda 1 plus lambda 2 plus lambda n. So we have covered this also during the basic probability, right? The additive property of the Poisson distribution. Now, so in your course, we have the multiple type of the queues, but in your course, we have only the Poisson queue. What is the meaning of the Poisson queue? The queuing system in which arrivals are Poisson process. Arrivals are in Poisson process with the mean rate lambda, that is number of arrivals of customer in any interval 0 to t of length t has Poisson distribution with parameter lambda t, and time taken by server to service a customer is exponential with parameter mu. Such queues are called the Poisson queue. What is the inference of this? Means inter arrival time follow the Poisson distribution with parameter lambda, and service time also follow inter-arrival time follow the exponential distribution with parameter lambda, and service time also follow the exponential distribution with this mean rate, right? Mean service rate mu. Then we say it is the Poisson queue. If the inter-arrival time as well as service time follow the exponential distribution, then we say the studied Q is the Poisson Q. Now we have the few theorems before starting the actual Poisson Q. Now first theorem is theorem 7.1. It is as it is from your book. If the number of occurrences xt of a certain event in any interval of length t, say 0 to t, satisfy the axiom of Poisson process with mean occurrence rate lambda, then inter-occurrence time are independent exponentially distributed random variable with same parameter lambda. What is it state? It states that over the interval, if if the occurrences of events, right, if the occurrences of events xt follow the Poisson distribution with parameter lambda t, then inter-occurrence time, inter-occurrence time, inter-occurrence time, inter-occurrence time, inter-occurrence time, this inter-occurrence time are independent and follow the exponential distribution with same parameter. So in this case means inter-occurrence time follow the exponential distribution with same parameter lambda. If the occurrences follow the Poisson distribution with parameter lambda, then inter-occurrence time follow the exponential distribution with parameter lambda. Clear this part? That's why I have written in the previous slide, right? Here the inter-arrival time follow the exponential distribution with parameter lambda. Since here it is given to you, arrivals are in Poisson process with mean rate lambda. So inter-arrival time follow the exponential distribution. Now, vice versa theorem of this, theorem 7.1b, if inter-occurrence time of independent exponential variate with same parameter lambda, then xt, the number of occurrences in any interval of length t, say 0 to t, will satisfy the axiom of Poisson process with mean rate of occurrence as a lambda. Here the thing is what? If inter-occurrence time follow the exponential distribution with parameter lambda, then the occurrences of the event follow the Poisson distribution with parameter lambda into t. Means if inter-occurrence follow the exponential, then occurrences follow the Poisson. If occurrences follow the Poisson, then inter-occurrence follow the exponential. So these theorem implied that if the inter-arrival times are independent exponential variate with the same parameter lambda. Now we are talking that if the inter-arrival time follow the exponential distribution with parameter lambda with the same parameter lambda, then number of arrivals in an interval of length t, say t1 to t1 plus t, that is the xt, has the Poisson distribution with mean or with rate, right, with mean lambda into t. Then lambda is known as the mean number of arrivals per unit time. That is the mean rate of the arrival. At that time, this lambda is termed as mean arrival mean arrival rate. Mean arrival rate. Similarly, we can define for the service also. So now, if the time taken by server to serve a customer is exponential with parameter mu, then assume that in independence of the service time for a different customer, the service time of consecutively served customer by busy server can be taken as inter occurrence time for the event service completion by the server, which by above assumption are independent exponential variate with parameter mu. Hence, the xt, the number of service completion by server who remains busy throughout the interval t1 to t1 plus t and t1 greater than 0 of length t has the Poisson distribution with parameter mu t. Means it is given to you here what they are saying, that here if the service time follow the exponential distribution with parameter mu, then the number of served customer number of served customer number of served customer will follow the Poisson distribution with parameter mu t. Served customer in interval in inter, in interval t in interval t, right, follow the Poisson distribution with parameter mu t. Clear this part? It is the same theorem. Now, in a multiple server queuing system, if the service time of different servers and for the different customer are independent exponential variate with parameter mu each, then xt, the number of service completion by n servers who remain the busy during the interval of length t will have the Poisson distribution with parameter n mu t. Here we what we have, let we have the server 1, server 2, server n. We have the n server and they are providing the service in parallel, and all all have the mean service rate mu mu. So so xt1 follow the Poisson distribution with parameter mu t, number of customers served in an interval t, in an interval of length t. xt2 also follow the Poisson distribution with parameter mu t, and xtr also follow the Poisson distribution with parameter mu t. Then if you define x as xt1 plus xt2 plus xtr, so just now we have seen the additive property of the Poisson distribution. So it also follow the Poisson distribution with parameter mu t plus mu t plus mu t, or you can say it is the n mu t, right? So from here, now the xt, now the xt, this xt is nothing, it is the sum of xt1, xt2, xtr, right? So xt denote number of served customer by n servers. Xt denotes here the number of served customer by, what did denote, number of served customer, served customer by n servers. N servers. So we are saying that it follow the Poisson distribution with parameter n mu t. So the service time follow the exponential distribution with parameter n mu. Then the service time follow the exponential distribution with parameter n mu. So that is written here. Clear this part, right? Now, if t has exponential distribution with parameter lambda, then actually presently now we are studying why we prefer to study the Poisson Q only. We have many Qs, but why we prefer to study the Poisson Q only? What is the importance in the Poisson Q? So these theorem will state these things. So if t has the exponential distribution with parameter lambda, then probability of probability of a less than equal to t less than equal to b greater than probability of a plus c less than equal to t less than equal to b plus c, where c, a and b are positive. So you know that what is the graph of the exponential? This is the graph of the exponential, right? It is given to you. T follow the exponential distribution, right, with parameter lambda. Now t is here. This is the ft. Now let's say this is your ab. It is given to you. A and b are positive. So we know that what is this? This is the probability a less than equal to t less than equal to b. And let's say this distance is c. If this distance is c, then this is the a plus c and this is the b plus c. B plus c. So this will give you probability a plus c less than equal to t less than equal to b plus c. So from here, from the figure, we know that this area or probability is greater than this area. That you have to prove. So what is the physical significance of this theorem? Hence, when the time t, interarrival time or the service time, is more likely to be small or very large are less frequent. Means in this case either the small time or the larger time, right? Small time or the larger time are very less. On an average, every service take the average time near to the average time. It is a totally random, but it take only the near to the average time. So here, hence, when the time t, interarrival time or the service time, are more likely to be small or very large, value are less frequent. It is very less frequent. The exponential distribution, exponential model is appropriate whenever we have the situation that either in service or in arrival, it is the means interarrival time or the service time is very small or very large. Then we avoid the use of exponential distribution. Exponential model is not appropriate, right? It is appropriate when the service required for the different customer is almost of the same nature. Exponential distribution is suitable to model the situation in which wherein the customer takes almost same type of service, same nature of service, same type of the service, or same time it take, right? Same time it takes. So in which the server is required to do the same sequence of the service operation for each customer, then the actual service time for individual customer would be mostly close to mean service time. Yet it is the random, but mostly close to the mean service time. Then in that situation we prefer the exponential or the Poisson cube, exponential distribution or the Poisson cube. Their deviation from the mean on either side would be small, but large deviation from the mean would be almost improbable. Then exponential distribution for service time would not be suitable. If I'm saying that mean service time is 10 minutes. So if the customers are taking the service in 8.5 minute, 9 minute, or 10.5 minute, or the 11 minute, then you prefer the exponential distribution. If the customer is taking the 1 second, 2 second, or 1 day, 2 day, then if we have this type of the situation, then we do not prefer the exponential distribution to model such kind of the service time, such kind of the service condition. We prefer the exponential distribution to model the service time, service condition, when when the customers take on an average same or near to the mean service time. Now, this theorem already you have studied for the exponential distribution. Memoryless or Markovian property of the exponential distribution. If t has exponential distribution with parameter lambda, then probability of t greater than t naught plus t1 given, this is the sign of the given, not right. T greater than t naught plus t1 given t greater than t naught is equal to probability t greater than t1, means this side is independent of the t naught, that is the memoryless. This side is independent of the t naught, so it implies that it is the memoryless. So let t be the time until the occurrence of event has an exponential distribution with parameter lambda, means let's say t the occurrences. So this t follow the what is the exponential variate. So at this time we have the occurrences, right? At this time we have the occurrences, so we say that t follow the exponential distribution with parameter lambda. The event has not occurred up to the time t naught. The event has not occurred up to the time t naught. The probability that the event will not occur in the additional time t1, additional time t1, that is the t naught and t1, up to here there is no occurrence. Occurrences is after that. Occurrence is after that, means t is the time of occurrences. T is the time of occurrences. So t greater than t naught plus t1, given that t greater than t naught, that we are writing. So uh, will not occur in the additional time t1 is independent of elapsed time t naught and is equal to the probability that event will not occur in the initial time t1. Clear this part? Means at that time we we are forgetting this time interval. We are forgetting this time interval. We are interested only for the remaining time, a time of study. So already you have proved this. So um, we have the probability t greater than t naught given t greater than t naught. So here we have the t naught. Here we have the t naught plus t1. So t greater than t naught plus t1 and t greater than t naught. T greater than t naught. So if you have if you have the probability t greater than t naught plus t1 given t greater than t naught, it can be written as probability t greater than t naught plus t1 intersection t greater than t naught upon probability of t greater than t naught. And what is the intersection? Here the intersection is here the intersection is this one, right? T greater than t naught plus t1. So probability t greater than t naught plus t1 upon probability t greater than t naught. So that is written here. Probability t greater than t naught plus t1 upon probability of t greater than t naught, which can be written as numerator can be written as 1 minus p t less than t naught plus t1 upon 1 minus p t less than t naught. So this is nothing. This is the CDF. So 1 minus CDF at T naught plus T1 upon 1 minus CDF at T naught. And we know that CDF for the exponential variate. CDF for the exponential variate is 1 minus e to power minus lambda t. That is the CDF of the exponential variate. So here we have written 1 minus exponential of minus lambda into t naught plus t naught plus t1 upon 1 minus exponential of the lambda t naught. So 1 and 1 cancel out, 1 and 1 cancel out. So here we have the exponential of e to power minus lambda t naught plus lambda t1, right, upon exponential of minus, right. So exponential of minus lambda t naught. So this lambda t naught and lambda t naught will cancel out. So here we have the exponential of minus lambda t1, that can be written as 1 minus f of t1, and 1 minus f of t1 implies that probability t greater than t1, that is the RHS. So here we can infer that it is the independent of t naught. It is independent of t naught. That is the forgetfulness Markov property or the memoryless property. The above property may be reworded as in the following theorem. So the same theorem we have. Suppose that interoccurrence times for some events are independent exponential variate with parameter lambda. Let t denote the interoccurrence time. T denote the interoccurrence time. Suppose that suppose that certain times t naught has elapsed after after an occurrence, and the event has not occurred during this period. Let r t naught is t minus t naught denote the remaining time until the next occurrence. Given that the event has not occurred up to the time t naught, then r t naught has the exponential distribution with parameter lambda. what is the thing? Let's say occurrence is occurring here, and this is the t, and this t follow the exponential distribution with parameter lambda. Sometime somewhere we have the t naught. So till t naught there is no occurrences. So this remaining time is the t minus t naught, right? So here we are defining the r r t naught as it is equal to t minus t naught. That is the remaining time. Remaining time, given that given that up to the time t naught there is no occurrence. Up to the time t naught there is no occurrences. Clear? So now we have to determine it is the what? It is continuous random variable. So we have to determine the PDF of the this random variable. We have to determine the PDF of this random variable. For the PDF of the random variable, what we have computed? Here we are computing the CDF of the random variable. Probability R T naught less than equal to T. So probability T minus T naught. R T naught is what? T minus T naught less than equal to T. Given that given that there is no occurrences up to the time t naught. So clear? Now this t naught, if you take on the right hand side, so probability t less than equal to t plus t naught given t greater than t naught, so probability t lie between t naught and t plus t naught divided by the probability t greater than t naught, and thereafter you can see it is the CDF of the exponential distribution. CDF of the exponential distribution. Clear this part? Clear this part? Here what we have, let's say it is the t naught, it is the t, right? So this time is the t minus t naught, and up to here there is no occurrence. Occurrence is coming at this point. So if you have to compute probability of t less than equal to t plus t naught, probability of t less than equal to t plus t naught given t greater than t naught, it means t greater than t naught, and t greater than t naught plus t naught, right? So what is the intersection? Intersection is this time. So it will become probability of t less than equal to t plus t naught intersection probability t greater than t naught divided by the probability of t greater than t naught. That is the probability t naught less than equal to t plus t naught upon probability of t greater than t naught. So it is the f of t plus t naught minus f of t naught upon 1 minus f of t naught. Clear this part? So the same thing here we have the memoryless property, means it is independent of the elapsed time. So other theorem we continue in the evening, and in the evening I will start the birth and death process, which is the basis of the King theory. So evening class is important class. So in that I drive the basic formula of the King theory. If you feel any doubt from the today's lecture, please ask.